Hey all, how are you doing?
Good. How about you?
Great question. I've got something going on this weekend where I'm supposed to do a lot of organizing, and I hate organizing, but I'm finding I'm getting it done, so that's a good thing. Um, I was just looking at our syllabus. My gosh, it's like the last day in week 4 of our 5-week course, and so just looking at that syllabus, we should be finishing up content in chapter 8 today. And that leaves chapter 9, 10, and 11. That's a lot of stuff for 3 weeks. Or no, not 3 weeks. Three class sessions next week, 1 week per chapter. But what I do know is we're not doing all of 9, all of 10, and all of 11. It's rather selected high points, the most important things that need to be covered. And to be honest, all good stuff. And yet, if something had to drop by the wayside, I've got a plan. Okay. We're going to get through what will get you what you need to move forward as engineers. And so, highest priority things first as we go for the rest of the term. So, I'm happy. Let's think. Maybe, are there any administrative questions? I do remember chatting with a student yesterday about one of the homework problems where it looks like all of you got half a point off, where I don't believe any of you should have received half a point off. I haven't checked with every single student, but I believe the grader may have misread one of the answers and then just marked everyone incorrectly accordingly. And I've yet to ask the grader to make all of those changes. And so that should be happening. And if you discover an issue, like we had a student yesterday ask me, hey, what about this problem? It seems to have been marked wrong. If you think that the answers provided, okay, in built into the homework assignment, don't match the score for any reason, or if you don't understand why that answer that was provided as correct was correct, it could be that there was an issue with the answer booklet. Okay, and so yeah, alert me to those issues, and I want to get it fixed for everyone and draw your attention to corrections that would need to be made, if any. Okay, so how about administrative questions of any sort before we move forward? Okay. Any subject matter questions from recently assigned homework problems, or maybe the lab from yesterday? Okay. Well, what I'd like to do is to move forward in the material, and let's think. Screen, boom, share that, go. Come on. I pressed the button, I thought. Okay, it seems like action happened. A change was made. Okay. I don't know how quickly we'll go, but I do know that this portion of the class content goes best when you all tend to just raise your hand virtually, maybe put something in the chat window. So I'm going to try and open up the chat window just to see if you do have questions, or just unmute and stink and talk. This material goes best for student learning when y'all do get involved and ask questions as we go if we have them. I know that depending on your nature of your personality and other things, and the nature of your discipline, and most of you are like engineers, what we find is some students are a little reluctant to ask a question when asking that question would have clarified something really important really early. And so if there's something that you're saying, I'm not quite getting it, definitely ask right away, especially today in class. Okay. So wait, maybe I'd like to dot an I and then cross a T before we move forward into newish looking material. In fact, what I'm about to do, dotting the I, is actually new. But it's revising something that we had talked about yesterday. And the crossing of the T, again, it's going to be revising something we sort of hinted at 2 class sessions ago, and then yesterday as well. Okay, so let's talk about the independent samples t-test. And that's by contrast with, well, independent samples, by contrast with the paired method, which is the next topic that I, dot the I across the T. The T is the paired. My hypothesis, if I'm going to state it in a statistical way, the best way to maybe state it for y'all as engineers might be that mu1 minus mu2 is some specified delta, and I'm going to call it delta naught. That's the delta according to the null hypothesis. Now, typically, delta naught is 0, and if mu1 minus mu2 is 0, that's another way of saying the two population means are the same. But in some cases, your null hypothesis might be that mu1 is exactly 5 units higher than mu2, so mu1 minus mu2 should be 5. Okay? The alternative hypothesis, well, we've focused on one of 3 plausible forms of an alternative hypothesis. One of them is mu1 minus mu2 is not equal to some delta naught. Okay, so that's the one we focused on the most. Equality versus not equal to. A second, however, alternative is that mu1 minus mu2 is greater than delta naught. A third one would be that mu1 minus mu2 is less than delta naught. Okay, so these are 3 possible alternatives. Some words that might go with the natural question that specifies any of these particular alternatives. Okay, is mu1 greater than mu2? Okay, if mu1 greater than mu2, that's your natural plain English question. I would say mu1 minus mu2 should be greater than 0. That's going to be the alternative hypothesis you'd want to use. And again, it's a yes or no question. So it's going to be a hypothesis test. Okay. So how about is mu1 less than mu2? Again, with a delta not being 0, mu1 minus mu2 might be negative. Okay. So mu1 is less than mu2. Okay. Is mu1 different from mu2? Okay, so depending on the nature of the questions you have, you might want to simply say, hey, is there a difference versus is there a directional difference? Like, does this mean larger than, or does this mean smaller than the all other of the 2 that we're comparing? Okay. So in this context, with these 1, 2, 3 alternative hypotheses, your test statistic is always the same, but your p-value will be a little bit different. So let's clarify what the p-values are going to be according to each of these alternative hypotheses. And, I would love to have some sort of ability to like erase a whole sort of a rectangle, okay, that I could draw on the screen. Maybe there is such a method and you've seen your other instructors do that. If you know about it, let me know and I'll know to look. Otherwise, I'll do this stupid thing that I keep doing, okay? My test statistic T is always a comparison of our difference of the sample means. And because I've got the order 1 minus 2, I'm going to go with the same order in my test statistic T. X bar 1 minus X bar 2 minus delta according to the null hypothesis. Again, usually 0 in value. And then we're going to divide that by what I'll term the standard error for the difference. And that standard error for the difference, let me just give you an equation for it now. SE for the difference is equal to the root of S1 squared over N1 plus S2 squared over N2. Okay, so we're home free. You've got a method, you've got a test statistic, and I guess all we need is the p-value from which we can get our conclusion. So let's go ahead and maybe again erase the pink bits. because I don't want the pink bits anymore. I want to draw something new for you. Okay, so let's pick a different color. And maybe I'll go with a bluish. Nah, I don't like the blue anymore. Let's go with a purplish of some sort. Okay. Depending on the alternative hypothesis, you're going to have your p-value correspond to something at least as extreme as what we did in fact see if the null were true, but at least as extreme in the way that causes me to want to believe the alternative hypothesis. So if my alternative hypothesis is this third choice, my p-value, and I got to give you, I guess, three different p-value approaches. The third p-value approach, you're saying, okay, alternative hypothesis here is mu1 minus mu2 is less than 0 or less than delta naught. I'm thinking it's going to be a lower tail. Okay, so yeah, literally we did see a particular difference of sample means that gave us a test statistic T. Okay, and for that test statistic T, something more extreme would be even more further into that region below delta zero. So mu1 minus mu2, instead of just being negative, we're saying, well, what if x bar 1 minus x bar 2? What if x bar 2 was even larger than what it was? Or perhaps what if x bar 1 minus x bar 2 was even further into that negative region? The lower tail area, the area below the value of t, is going to be your p-value. In this second case, okay, your p-value would be, as you might suspect, oh my gosh, horrible curve. Your p-value would be, like you might suggest, still a bad curve. Darn it. Third time's the charm, they say, right? Okay. It's going to be the area under the t curve from t and up. Okay, so it's a upper tail test, if you will. A lower tail test is that third one with a less than. Less than is a lower tail. Greater than is an upper. A not equal to alternative hypothesis is a two-tailed test. And I apologize here for getting rid of part of this equation. Maybe I'll just get rid of all of it for completeness. And let's show you the third approach with the two-tailed test. And to be a little bit careful here, I'm going to say whatever the value of t is, there's a negative and a positive of that. So let's go with the absolute value of t and up, or the negative of the absolute value of t and down, which is the approach that we took yesterday when talking about a p-value for an independent samples t-test. JMP will give us all of those exact approaches. Okay, so let's maybe go ahead and use a data set that I think, which is the one that we used in class? Oh, Bumpus. Can I even find Bumpus? Found blackbirds. You know what? I'm using the Bumpus data set here, and this is sort of like what you saw. And let me here move this off to the side, and move this off to the side. Take a picture, and then clear it, and then show you the Bumpus data set. My null hypothesis is that the birds that survived and the birds that died weigh the exact same amount. The alternative, on average, the alternative is that the amount that they weigh is different on average. Okay, so that would be a way of going under analyze fit y by x. You would say, is the weight different between the two statuses, the living and the dead birds? And we find the dead birds a little bit less than the living birds on average. If I turn on the means and standard deviations, I have all the content with n, x bar, and s to do my hypothesis test. But we could also just go ahead and turn the t-test on. And that t-test over here says, we get these 1, 2, 3 p-values. 1 is the probability greater than the absolute value of t. That's these two areas taken together. And if your alternative hypothesis is that the living and the dead birds have a different average weight, then your p-value is 0.0327. If your alternative hypothesis, however, is that the living birds are larger than the dead birds, the survived minus died means mu survived minus mu died. We can estimate that as 0.8. My upper tail area is 0.0163. So in other words, my p-value is half that of the two-tailed p-value. Indeed, your alternative hypothesis defines whether your p-value is two tails or just the upper tail. And I would say if your alternative is that the living birds are larger than those that died on average, your p-value of 0.0163 says, oh my gosh, it's even less likely that I would have seen a difference this big just due to luck alone. What if, on the other hand, we had incorrectly, however, said, you know what, that the living birds should be smaller than the ones that had died? Your p-value would be a lower tail test. Your p-value would be 0.9837, and there's no way you'd reject that null hypothesis of equality in favor of believing that the living birds were smaller than the dead ones, when that's the exact opposite of the pattern we see here in the data. So usually of the three p-values presented in the context of a t-test, one of them is laughable, and it corresponds to, yeah, that isn't even following the pattern that the data are showing us. The two others correspond to, hey, is there a difference or not? Versus the other one, oh, is there a specified kind of difference? As statisticians, we have to say, unless you are biologically going to walk up and say, oh, yeah, survival of the fittest, the dead birds should be smaller on average than the living ones, unless you can tell me a hypothesis that's rooted in some other theory, you should probably go with a two-tailed test to assess simply, is there a difference between our groups? Okay. And that is really what we recommend. If, however, in your discipline, you think, oh, yeah, if I have 30% zinc and 70% copper, it should be a slightly softer metal than if I have 40% zinc and 60% copper. I mean, I don't know, soft versus hard for metals and alloys for anything to save my life. But I'm saying, if you tell me your natural question is, hey, is this alloy going to be harder than that one? You're telling me you want a one-tailed test. You're going to use one of those second two alternative hypothesis p-values. Any questions about that so far? So that was the dotting of the I. Let's cross that T. And in the crossing of the T, I'll do that in the context of the data we used last time, sunscreen. Okay. And so let's pull up the sunscreen data set. Let's see if I can even find it. Sunscreen tolerance. And here we go. We've got our control group and our sunscreen group, the two arms across these 13 different people. And we did a confidence interval previously. There is a corresponding hypothesis test. So let's go ahead and try the procedure, and it's under not specialized modeling and matched pairs. And I'm just going to say control and sunscreen. I'm going to slap them over together, both there. And the software by default says, okay, I'm going to pick one of your groups and then the other one to be your two different groups. And so sunscreen has a 309 typical amount of time in the sun before damage occurs. Control is 61. The difference is 248 minutes more. And our confidence interval was, you should be able to be in the sun 200 to 300 minutes more if you have the sunscreen on than if you're wearing a control suntan lotion. Let's just call that body lotion with no sunscreen, no zinc, no nothing in it. Okay. You might have spotted, though, there was this test statistic T there. What is that test statistic T doing? In the context of paired data, P-A-I-R-E-D data, tests of means. And again, your thought is we're going to look at differences, which is the first reading minus the second reading. You know, you might naturally want to switch sunscreen and control, in which case you could just put them in the other order, or just change the signs to negative if it's the degree, direction other than what you were thinking of. You're going to calculate for each difference. Okay. You're going to calculate the difference itself. You're going to find the average of the difference, the standard deviation of the differences, and also the number of differences. And your test statistic T is going to correspond to D bar minus a delta naught. Again, a specified difference that you would expect to see according to the null hypothesis. So that says our null hypothesis has to be mu D is that specified delta naught value. Okay. And then we're going to divide it by the standard error of D bar minus delta naught over SD over the root of ND. That is, again, the denominator as a whole is the standard error for D bar. In terms of how well does D bar, how precisely does D bar estimate mu D? It's off by about that denominator or so. So our null hypothesis is mu D is 0. There are 3 alternatives, and they correspond to 3 different natural questions. There's mu D is not equal to delta naught, that the average amount of time in the sun is different if you're using sunscreen than if you're not. Okay. Mu D might be positive, maybe larger than 0, or delta naught if it's not 0 that you're comparing to, or mu D is less than delta 0. Those are your 3 alternatives. And I'm thinking in the context of sunscreen, you're inventing this stuff because you think it's likely going to allow people to not have as much sun damage, so the time to damage will probably be larger. The alternative that makes sense here is, can you be in the sun for longer if you use sunscreen than if you don't? Okay, there you go. That is your alternative hypothesis. And our alternative hypothesis has a p-value that goes with it, but let's, for completeness, show you all 3 p-values. The p-value is going to be one of the following 3. It's going to be a 2-tailed area below the negative of the absolute value of t, or above the absolute value of t. The second one is going to be a upper tail area, so above t, whatever it was. And in this case, RT here is like 10. That is a tiny upper tail area, and you would say, no way could this happen just by luck alone, if in fact the null is true. So let's rephrase. If the null hypothesis is really true, if sunscreen doesn't actually allow you to be in the sun for any longer before sun damage occurs, I would about never see what I actually did see in my data. I'm going to believe the alternative, that sunscreen helps. The lower tailed test, the less than alternative hypothesis, is going to be a lower tail area. Okay, so dotting some I's, crossing a T. T was the paired data, the paired data t-test. Dotting of the I was the independent samples, I for independent samples t-test. Any questions about this before we move into the last bits in chapter 8? Categorical variable testing or categorical data testing. Okay, so what I want to do is to introduce you to a completely new method. One we hinted at sort of recently, but let's be really careful to dot our I's and cross our T's and talk about what if we've got a binomial proportion. Okay, flipping coins. We want to know, is it 50-50, heads and tails? If there's only 2 types of possible outcomes, okay, and we just keep track of the proportion that are of one kind, let's call it successes or heads, my null hypothesis could be that the actual underlying rate of success, pi, is, and I'm going to call it pi 0. Okay. On the other hand, I can go with, well, pi is not, pi not, pi not, pi not, pi greater than pi not, or pi less than pi not. So those are our 3 alternative hypotheses. Our test statistic, like we hinted at yesterday, no, let's not call it P, let's call it Z. It's going to use P, but our test statistic Z is just what we see in the sample proportion. P is the number of heads over the number of trials, the sample proportion. We're going to compare it to pi naught. Okay. And so we have a numerator is a natural comparison, and we'll divide through by a measure of spread, which, if the null hypothesis is true, is the right one to use. Okay. And if you have a binomial population, okay, the rate of success, okay, P, should have a standard deviation of pi times 1 minus pi all over n. So I'm going to divide then by the root of pi naught times 1 minus pi naught over n, the number of trials. Okay. So here we have in the denominator, notice that there is in the denominator a value pi naught. It corresponds to the null hypothesis, because remember, our next step after the null and the alternative hypotheses and the test statistic, we have to sort of say, how likely is it that we would have seen a result like this if the null hypothesis were actually true? We have to assume the null is true to get our test statistic Z. Our test statistic is based on assuming the null is true. If the null is true, the distribution of this Z curve, the distribution of this test statistic Z follows a Z curve. Okay. And so like before, I guess I could calculate a test statistic. And if I had P is just 39 in 100 flips of the coin, 39 heads, P is 39%, 0.39. Pi naught could be 0.5. I might wonder if the coin is fair. My test statistic Z is 0.39 minus 0.50 over then the root of 0.5 times 1 minus 0.5 all over 100, all again within that root. And that gives me a negative 2.20. And I think I care just, is the coin fair or not fair? I don't want to know, hey, is the coin biased in favor of heads? You might, for your coin that you suspect might be biased in favor of heads. But I just want to know, hey, is my coin fair or not? So if your natural question, hey, is my coin biased? It might be different than your natural question, is my coin biased in favor of heads? Or is my coin biased in favor of tails? Based on the null and alternative hypotheses that you set in place before actually gathering data, you have defined what your p-value will be based on the data values themselves. So because we have a not equal to alternative hypothesis, I'm going to have a two-tailed p-value. So negative 2.20, so 2.20 and up, negative 2.20 and down is my p-value. And that says, how likely is it that I would see a result at least this extreme if the null were true? Let's get a quick p-value before we hit our conclusion about our coin. And I can do that. Maybe I'll go down a little bit so you can see more easily. Use the Z curve. Mean zero, standard deviation 1. That's the Z, the standard Z. And so all I need to know is that outside area, so Z below negative 2.2 or above a positive 2.2. And I have a p-value of 0.0278. Taken between these two tails. So in other words, if in fact the coin is really fair, if the coin's really fair, then 39 heads in 100 flips is a bit on the unusual side. It's unusual enough that it's below the standard 0.05 cutoff for our p-value. I'd say this coin is biased. You might want to compare it to a different level than 0.05 for your p-value. It depends on the context of the problem. We'll talk about that one later, but not today. I'm going to say you could have a different conclusion based on your choice to compare to a different alpha than my choice, the standard 0.05. Any questions about that? Other than, can you move that off to the side so I can read? Okay. So moving forward then into the last method that will tackle two different ways. Actually, I shouldn't say last method, two different ways. one particular distribution that we haven't seen so far, chi-square, and we'll use in two different ways to tackle two different sorts of questions. Let's just sort of maybe start down the path of chi-square with a simple problem. And I just want to know if my die is fair. I've got a dice, actually a dice. I've got a die, a singular die. And I want to know, is the die fair? Because I work for Bally's Casino in Las Vegas. And if the die is biased, I don't want to have that one out on the floor, because if someone discovers the bias, then I'm probably going to lose a lot of money. Okay. So I want to know, is the die fair? So and this will sound absolutely asinine, but I'm going to roll the die 60 times, and it's a regular six-sided die. And I've got a hypothesis, okay, that the die is fair. It's easy for me to believe it's a fair die because it looks like all the others that came off the assembly line, but I want to test this one. My null hypothesis of fair means, well, that the rate of getting ones is the rate of getting ones according to a specified distribution, 1 in 6, 1 in 6. The rate of getting twos is the rate of getting twos according to, again, my null hypothesis, and that should be 1 in 6. And I'm just going to draw the ellipses there all the way through. The rate of getting a 6 is the rate of getting a 6 according to a null hypothesis, and that is a 1 in 6 chance. My null hypothesis, if you will, is composite. There's lots of equalities here, and if any one of them is actually not true, then the null hypothesis is not true. There would be a bias in favor of or against one of the numbers. In fact, some of you might have thought, hey, if one of them is not true, I guess that means at least one of the others has to be not true. So your null hypothesis could be they're all the same in all 1/6. And the alternative, you could say it as at least one of the chances is not 1 in 6, or you could say at least two of the chances are not 1 in 6. Either way is correct. Okay. So here's what the data are suggesting. I mean, sorry, the data. Here's your null hypothesis, and this is only the null. The alternative hypothesis could be written as not that. Rephrasing that, if I wanted to put it symbolically, I would say, yeah, that's going to take a long time. But maybe saying at least one of those values for pi 1, 2, 3, 4, 5, or pi 6 is not equal to 1 in 6. That's valid. That's a way of writing the alternative hypothesis. So you'd want to collect data, and let's look at a hypothetical data set. Oh, actually, no. Before we look at the words, they elude me. What would you expect to see if you had 60 total rolls? 60 rolls, 1 in 6 chance for a 1 on any one of the rolls. You'd expect 10 heads. I mean, 10 ones. You'd expect 10 twos. All the way up through, you'd expect 10 results of a 6. And so you have to say, let's take our rates of the null hypothesis and multiply by the number of trials to get the expected count, the number you'd expect to see in each of these possible outcome states. Then let's actually look at what we did get, the observed data. And I'm going to call EXP for expected. Some of you think exponentiation. No, just expected outcome. Observed OBS for the observed outcome. And what if I had 3 ones for 4 twos, 17 threes, 12, 12, and 12 for the 4s, 5s, and 6s. Again, that sums to 60, okay? And I'm spotting maybe a bit of a difference here, that at least for the 1s and 2s and 3s, I see something sort of not even close to the 10 that I'd expect to see. These 12s, okay, they're not too far away from the 10s I'd expect to see. We have to come up with, however, a way of measuring how closely our data are to what the null hypothesis says we would be likely or expecting to see. Okay, so here's your chi-square value. And If you want to talk about chi-square and office hours, I'll just say, oh yeah, it's related to the normal curve, and I could tell you more about the history of when it was invented in the first couple of uses. But I'll just say this squiggly x or chi-square, that is the value of our test statistic, and it's just summing over all the categories. The observed count in the category, the observed count in category I, minus the expected count in category I, take that difference and square it, and then divide through by the expected count in category I. So we're summing across every single one of these possible six outcomes. Okay, and so what would I have here? Well, let's figure out maybe a column for the observed minus the expected count, and that would be -7, -6, 7, -2, -2, and -2. I think I got that wrong. I'm sorry. The 17 to 4. Yeah, no. Mm-hmm. The observed minus expected, these are +2s. Okay, there we go. So I have my observed minus expected values, and I guess I could square them all. And so then the previous squared, so that's 49, 36, 49, 4, 4, 4. That's pretty easy. And then if I just divide by 10, the expected count, I get 4.9, 3.6, 4.9, 0.4, 0.4, 0.4. And the sum here at the bottom is 14.6. Okay, so what do I do with that? Well, let's remember what our test statistic is supposed to do and ask ourselves a couple hypothetical questions. What is it supposed to do? It's supposed to measure how close our data are to what I should be seeing if the null were true and the expected counts was 10 in every case. If instead of, say, 3 and 17, I had seen 2 and 18, I'm thinking the observed would be even further away from that expected count. The value for chi-square would go up. Further away from the 10s that I expect to see is going to correspond to a larger chi-square value. Let's look at the other hand. What if I always saw 10s across the board? The value of chi-square would be 0. Small chi-square means I got exactly what the null said I should have gotten. The alternative hypothesis, if that were true, our value for chi-square will tend to be larger. Okay, and so how do we look up that value 14.6 and get a p-value out of it? Well, we also have the degrees of freedom. In this case, it's the number of categories, k minus 1. In this case, 6 minus 1. That's 5 degrees of freedom. And with our chi-square distribution, so we get our probability distribution table one more time. And let's erase, and darn it, I wish I knew how to erase like a whole block. Yeah, maybe there's a fancy way of doing this, but shapes, maybe I'll make a shape. No, that made it, but well, it's better than nothing. Let's go with a white shape. Hey, I learn a thing every day. Cool, I put a giant clear rectangle. Okay, that means I can drag this thing over here. Darn it, I can't because it's, yeah. Okay. Okay, so has anyone ever said that Zoom could be improved? I'm not hearing you talk out loud, so I'm assuming y'all said yeah. And what they went for recently is they now say, oh, we could put 1 million people in a Zoom meeting. And I've been in a Zoom meeting with like 50 people. And even everyone keeping their mic muted at the same time is a challenge. When you get 50 random people, it's like a mess. Okay. So bragging that we have the ability to have 1 million people in a Zoom meeting doesn't strike me as important as the ability to, within the screen sharing thing, to be able to just erase this whole rectangle all at once. So if any of you end up working for Zoom, give them my idea and tell them that that's what they need to do. So let's look for Oh yeah, we said just yesterday normal. We use that a lot. T a lot. Chi-square. Then F. These are the 1, 2, 3, 4 most commonly used distributions. Let's use chi-square here. And it says we need to know degrees of freedom. I had said 5 earlier, so let's just value of 5. Boom. And I want an upper tail area because the more the data deviate from the null hypothesis, the larger your chi-square is. So I want to know what's the chance of seeing a chi-square more than that 14.6 just due to luck alone. Could it be larger than that 14.6? And I need to change this so that way I'm not drawing in white on the board. Okay, so I'm going to plug in a well, I want an upper tail area, and I want 14.6, and that says only in about 1.2% of the time would you see results at least as extreme as the 14.6 that you did see. Your 3, 4, and 17 were just too far away from the 10 that you expected. That is a collection of values. Those 6 values say, no, the die is biased. You don't believe the null hypothesis of fair. You reject it. You believe there's something other than fair in your distribution. Any questions about that use of chi-square for the sake of looking for a relationship? No, for the sake of just comparing a distribution of outcomes to a set of hypothetical chances. Okay. One more example then, and this is one that dates back to, I don't know if any of you are NFL fans, but the year that Tennessee was in the Super Bowl, and I think they lost to the Rams when the Rams were in St. Louis. So you're thinking that was like forever ago. And Tennessee threw likely a touchdown pass to a wide receiver who was tackled right after time ran out, who was tackled half a yard short of the end zone. I've never seen it close to the Super Bowl that the last play could have completely changed the outcome. I mean, I guess in every case, the last play could change the ultimate score, but it was that close, as in the viewers, thought, oh my gosh, this is maybe going to happen here. Okay, so the best part about that game wasn't that the Rams won, and I don't really care about either team, but it was one of the commercials. The commercial was for a product called Xenical, and Xenical, their tagline was, "If you've been unable to lose weight by diet and exercise, ask your doctor about Xenical." And so then they have the voiceover at the end of every drug ad. You know, nowadays it's like it may cause death. Well, back in those days, 20 some years ago, the voiceover said may cause, and it was really super quick. I'm glad I heard it, but the voiceover said may cause an inability to control one's bowel movements. And I thought, oh, that's a side effect worth studying. So I went to Xenical.com and got the FDA study where they reported the data that allowed them to make the statement, hey, you might have explosive diarrhea if you take this medicine. Okay. So there was two types of people in the study, Xenical and then the control group. Okay. And they had, rather than asking the people, have you had explosive diarrhea in the last 3 months while you've been taking Xenical? They asked the question, have you experienced fecal urgency? Because I guess asking about explosive diarrhea is just a little bit too much over the top. So they asked about, have you experienced the condition of fecal urgency that I'll abbreviate FU? No fecal urgency, I'll call it NFU. And there were 1,913 people taking Xenical, 1,466 people taking the placebo. The rate of FU in the Xenical taking people is 356. And in the control group, it was 98 of the 1,466. 1,557 did not have fecal urgency in the one group, and then 1,368 didn't have in the control group either. Okay. Overall, I want to find out what's the answer to a question. And the question is the rate of fecal urgency the same in each group? Okay, so my null hypothesis, that's going to be like a yes/no question. Is it the same? Well, the same would correspond to inequality. my null hypothesis could be stated: the rate of, or the chance of, fecal urgency in the Xenical taking group is equal to the rate of fecal urgency in the control group. And I'm just going to call that value pi. I don't know pi, but I can calculate pi hat. That's the overall rate of fecal urgency, and that would be 454 of the 33,789 individuals. 454 of 33,789. In this case, it's 0.134. If I wanted to round even further and have more precision, great, I could. You could do it. Okay. So what should the data have looked like if the null hypothesis were true? If the rate is the same in each of the two groups, if in the first row and in the second row the same rate was evident, and if that rate was 13.4%, what should the numbers be I'd expect? So I can derive an entire table of expected counts. So here are the observed, what I did see, the expected counts, EXP for expected, Xenical and control, and fecal urgency, FU, and no FU. And what should be the numbers I'd see? Well, of the 1913 individuals who did take Xenical, if there was a rate of 13.4% of them experiencing fecal urgency, I'll just say 1913 times then that 454 over 3379. That's going to be 257.0. I would see 257.0. Now, some of you are wondering why the 0.0? Shouldn't you see like a person either in that category or not? No, this is just what you would expect to see in the long run with this rate of occurrence. So a 257.3 could have occurred. It just happens to be, in this case, 257.0. I'm going to include the 0.0 just to remind myself that values for expected counts that aren't integers are completely allowed. So if I have 1913 people trying something and I would have expected 257 to have experienced fecal urgency, I would have expected the rest to have not had fecal urgency. So that's a 1656.0. And then what about that second row? Well, I could use the same trick and say 1466 times then the rate of 454 of 3379. And that gives me an expected count of 197.0. 197.0. The expected count in the lower left cell. Some of you might have already seen this method or just noticed that yeah, literally the sum of 257 and 197 is the 454. The row totals must match. The column totals must also match between your expected and observed tables. That last expected count, and I'm going to put it here in pink, is 1269.0. And I've got a set of 1, 2, 3, 4 observed and a 4 expected counts. I could go ahead and calculate the chi-square value here in this situation. Do any of you need me to pause for a second while you write it down real quick before I go to the next page? Or are you saying, hey, I could just, rewatch this and I know it's going to be with like about 2 minutes to go? Okay, cool. So I'm going to go ahead and I stalled. I'm moving on. My chi-square value is just summing over all the categories. The observed in that category minus the expected count in that category squared over then the expected count in that category. And in this case, the upper left cell would have been a 356, but I expected 257.0. I'm going to square that. And then there were the two values in the upper right and the lower right, lower left and lower right. And my sum is, in this case, 101.3. So is that going to be a value that gives me a small p-value, 101.3, from our chi-square distribution? Well, I need to know the degrees of freedom equals what? Earlier you said, Steve, degrees of freedom is the number of categories minus one. Okay, that's for the earlier method if you've just got one column of counts. If you've got rows and columns, the degrees of freedom is equal to the number of rows minus one times then the number of columns minus one. In this case, it's 2 minus one times 2 minus one, and that's 1 degree of freedom. So let's grab our chi-square distribution calculation tool, and I am sorry for this, the overlay here. I'm going to put in 1 degree of freedom, boom, and put in my chi-square of 101.3. And the chance is like never going to happen. Let me rephrase that. Your p-value is like 0. Not exactly 0, but really close to 0. If, in fact, there is no relationship, if the rate of fecal urgency is the same whether you're taking the placebo or the control, the placebo or the actual medication, I should say, then I should never see counts like I did see considerably higher rates in the Xenical taking than in the placebo taking group. So in this case, I would reject the null hypothesis, believe the alternative. So let's talk about the lab that you guys are going to face. You're going to look at it. It's data like this, chi-square, tabular data, and I'll just stop sharing the screen, and I'm going to note that it feels disastrous, this lab, because you got the Donner Party, and if you haven't been in a class which studied the Donner Party in 4th grade, like if you're out of state, have someone in your group explain to you about the Donner Party or read the Wikipedia page on it. And then the Titanic is the other data set. And what we're really looking is for a difference in the survival rates in each of the two disastrous contexts. But we've got the two types of people. They were classified as M's or F's when the Donner Party sort of left. And so you got the 2 rows and then died and survived. Same thing for the Titanic. Or in the case of the Titanic, maybe there's, crew, 1st class, 2nd class, 3rd class passengers. Maybe there's more than 2 rows in your analysis. But, that's for you to figure out as you go through the lab. Good place to stop. I'm going to stop the recording after I give you the chance to ask any last-minute questions. Otherwise, enjoy your afternoon and weekend. Any last questions? Okay, cool. We'll talk to you soon. Bye-bye.